So let's demystify the controller Gerard was talking about into this washing machine BLDC motor. So everybody knows that. So this is the... Let's start from hardware, okay? So we will run this one. So you can see this is a standard winding. I think this is the wire is around 0.8 millimeter, about 90 winding, 90 turns per slot, and of course that's a 24 pole pairs, because every single magnet has four poles. So altogether is a 48 poles, so 24 pole pairs, and we have 36 slots. That's the slots, right? So this is something like this one. This unfortunately does not have specification printed on the drum. This is very similar. It's not the same, but it's very similar. So this is what they say. Well, like this. Okay. 310 volt DC, 0.6 horsepower, 2 amp, 1400 RPM. So the question is, can we run at least this 1400 RPM with 310 DC? Well, my answer, and I will show you that, is yes and no. Okay, so this is a drum. This is a driver you can build. So what's that? What is it? Let's start from here. So this is 240 going through the filters. Very simple, like NTC. This NTC is a little bit too strong because it's a 20 ohm. Then AC filters. This is rectifier and capacitors and DC coming into here. So as you can see here, maximum 400 DC is coming here. So normally when you connect into 240, you will have like 330 DC on input. And this box, it's just a DC power supply, 18 volts, because you have to feed this electronics here. So as you can see, here is a VCC 20 volt max, and we're using 18 volts. So this is power stage from ST Electronics, Stival IPM 15B. So that's 1500 watts power supplier, power stage actually. This is controlled by this controller. I use this one for the reason it will. I'll show you why. And we're running this process microchip Nucleo F446RE, and this is connected to the computer, and we will run the program, and I'll come back in a second. Last piece of hardware you need to have is this USB isolator. So this is something like this. It's quite cheap. It's like 12 pounds or something like that. You can see USB to USB. That's the only thing I can understand from here. And it could be this one, could be that one. USB isolator, right? And why is that? Because you have, on power stage, you have quite high voltage here, and it's connected, you know, USB, and you don't want to connect directly into your laptop. Yeah. So you just need to run it through this one. So we'll connect that, and it's already alive. And this is a software we will use, ST Motor Control Workbench, and so on. Okay. From here, we will go to Motor Profiler. So this is very nice software, which will profile our motor, which we don't really know all parameters. So we know that we have 24 pole pairs. We want, as they say, 1400 RPM. Max current, they say 2 amps, but let's do 2.5 amps. And V bus, we'll leave it here. So this is something between 7 and 400. But first, actually, we're supposed to select boards. So not all boards which are available from ST Microelectronics, they supporting this motor profiler. So this is the reason why I choose Nucleo F446RE and IPM15B Stival. So we will go 446RE, there you go, and power board 15B. Okay, so we have a pair, they are active, all good. There you go, and it's ready. So this is fed. Oops. This is fed. Power supplier goes into auto transformator. So now it's quite high voltage. We don't want that kind of high voltage because I want to show you something. So let's go back down into 220 volt AC. Okay. 220 volt AC. We will fed into this one. So that will be about 300 DC on the input here. On the input, right? Okay, and let's start profiling. So once we will connect to the board, and now we'll see the information. There you go. Firmware upgrade required. Why is that? The reason is because there is a different firmware already in a chip, and the firmware needed for profiling is different, simply speaking. So we need to do upgrade firmware. Sorry about the focus, I can't do anything about it. So there you go, everything is ready. So start profile. It's doing something. Yeah. So already we know that electrical model 3.9 ohm, 17.5, and this is VRMS. You see the V bus here, 299 volt DC, and this is 2.5 amp we set up. So this is back EMF measured from the motor. And funny enough, you know, it will be a little bit different in a moment, but you will see, you know, on average is 300 something volt per 1000 RPM, KRPM. Can you see the max speed? 620 RPM. And we have a friction, inertia, that stuff. You see, this is maximum speed we can get on this voltage, which is now went down. It was about 300 volts. Why you know it dropped from 200, almost 300 to 283? It's because of this one, this NTC, which is a little bit, it's not charging fast enough, but you know, just an average. So you will see, you see that that's all we can get. So okay, that's fine. Let's do disconnect. Remember this one, 620 RPM. And let's give him a little bit higher voltage. Let's get up to 280. Yeah, 296 volts. AC, which will be 300 something, almost 400 DC in here. So let's connect it again. USB. Okay. Okay, and start profile. $390 DC. And what we can see here, we already have 820 RPM comparing to 620 RPM. But also, can you see this one? Before it was like 300 VRMS, now we have 360 VRMS. I just raised the voltage. So you have to average that, yeah? You can measure it, you know, you can measure back EMF, this KE value, you can measure it by spinning the motor by hand, or, you know, drill or whatever, and measure it on an oscilloscope. But, you know, this is really nice tool to see what's going on. So you can see it's 800, it's almost, yeah, it went down. So, yeah, but it's like almost 400 volts and 800 RPM. Nowhere close to 400 RPM, 1400 RPM. So why is that? So why they say that this motor is running on 1400 RPM? Well, because it's a washing machine, they doing a trick which is called flux weakening. And we will come back into this in a moment. So let's, okay, disconnect. Okay, come back in a sec. So here we have a project using this hardware. So let's click on the motor, and you have to configure, because normally if you would just use the motor from the profiling, you would have, you know, 820 RPM or something like this. And nominal DC is 311. We don't like it. Let's do 360. Yeah, why not? And 1100. Let's leave 1100 RPM for now, because this is more than 800 RPM anyway. And let's do nominal current 3 amps. That's fine, and the rest is fine. So done. And now, you know, and here in drive management you have something like additional feature. So here we have, you have to tick this box, flux weakening. And for, it's not enough, you know, obviously it's not enough to just do flux weakening. You have to configure these values here, but that's completely different stories. For now it's just, let's try to run it more than 800 RPM. Why they say, you know, 11 or 1400 RPM with 300 something volts. So I just want to show you what's possible with and without. So without, I already showed you, it's like almost 400 RPM. It will give you, almost 400 volt DC. It will give you around 800 RPM with this motor, and no more. You can't do it because of the back EMF from the motor. Yeah. But you can use this flux weakening, and let's see if we can do. So now I will have to configure everything and transfer firmware into the controller, and I'll come back in a second. Okay, firmware is already transferred, so now we will use MotorPilot, and we'll connect to the board. Connect. Let's see, 1100, 10 amps, and okay, so let's quickly configure all of this. Reload, change these values, 0.4 for shunt, and this actually op-amp gain is 2.1 for this board. Okay, and go back. The screen is small, so I have to go back and forth. So just bear with me. Application configuration, we want not 10 watts, that's not enough. Let's configure for 400. This is what I've done just now is just this value here, power, right? So we will see from 0 to 400 watts of power, what application is taking, power stage, and advanced configuration to see some values here on the right side. And we will start from 400, 350. Let me see, this is Reverb is set up for 350, so 350 RPM. Then we will go for 500 in slowly, with not rushing. So okay, it's all good, and start. There you go. Okay, so now we have mechanical speed 348 RPM. Okay, so let's speed it up to 500. Cool, works. How much volt do we have? We have 375 volt DC. Okay, let's go to 600. $700. $700. $800. So we're coming to the point of amount of RPM we can get without flux weakening. But because in this project I configured flux weakening, as you can see here, flux weakening enable, right? Then I can go further. 900 RPM. Yeah. 900 RPM. Let's go for 1000. Yes, we got it. 1100. We have 1100 RPM, mechanical speed, and it takes 350 watts. Can we go further? Not at the moment, because I configured only for 1100 RPM. So even if I will do 1150, I won't get anything because it's not configured, right? So slowly, let's go down. Ah, okay. Let's go back to 1100. Let's confirm. Oops. That's because, you know, it jumped into 1200 because it's not fully configured with speed regulators over here. But that's completely different story. Now we're just showing that we can get more speed for a voltage which allows us only, you know, like 800 RPM. We can get 11 and 12 and maybe more. And let's confirm that. It's 1100 RPM. Yep. Okay. So now the problem is that back EMF is so strong that if I would all of a sudden flux weakening algorithm would stop, it would most likely blow the power stage, because all the voltage will go back into the power stage from the motor, and it will be boom, disaster, right? So I will go slowly. So that's fine. 400. So the question would be, can we, for 400 volts, can we get 3000 RPM? I don't know. I don't think so, to be honest. I don't think so. I don't know. But here's a problem with flux weakening. Okay. Here's a problem. So what's happening when a motor spins? Yes, the faster it spins, the stronger back EMF is growing. So if you have enough voltage to counteract the back EMF, you can still run some amperage, some current, and spin your motor faster and faster and faster to the point where the difference between your V bus and your V EMF, back EMF, actually is a B. It's quite difficult for me to write it looking on the phone. Back EMF. It's almost the same, and no current flowing, so you don't have any torque, right? So it should be some difference. So that's why you remember KE. It was something between 360 volt RMS per kRPM. So let's, more or less it will be like 300, let's say 330 volts. It creates per 1000 RPM. Yes. So in theory, if your V bus would be 330, you would get 1000 RPM, but with zero torque, really, right? So you cannot spin the motor, and so hence it has to be some difference between V bus and back EMF to still have some torque and spin the motor. So that's why we have around 400 volt DC, and that gives us 800 something RPM. So you can calculate what voltage, that's the wrong sign, what voltage you would need to have to get 3000 RPM. Just calculate that and you will see X, how this X is. Actually, I'll do it. Can't remember. Calculator. So it's 400 multiplied by 3000. Yeah, divide by 800. Can you see this value? So I would suggest that you would need to have 1600 volt DC power stage to run it without flux weakening. So in theory, you can have half of it, or maybe like 1000 volt DC, configure flux weakening and still run it on 3000 RPM. That's the trick. But here's the problem with flux weakening. Normally, what's happening, you have speed and is it speed? No, that's wrong actually. That's RPM, yeah, RPM. So it goes into, in our case, into some value, which is, in our case, 800 RPM. And the torque goes more or less like this. Sorry, more like this. Yeah, it grows very quickly up to maximum value, and it keeps that way. So once you apply extra power to counteract back EMF, and you're going from 800, you're going to, let's say, 1400, yeah, RPM. So you're going like that, you hit 800 and you're going to 1400. The torque goes like this. Ugh. Sorry, it's really difficult. Like, yeah. Let's do this way. Just like that. 18, 14, 800, 1400. So it goes like that, and the torque actually goes like to some maximum value, and it keeps that way. Then you kick out your flux weakening, right? And the torque goes down. Okay, so you still have some power, yeah, because the power is torque multiplied by speed, but it's not the same torque. It's not the same torque value, because you're weakening the field. So this is the problem with flux weakening. So yeah, actually that's it, really. Yeah. So one more time here. 400 volt DC, 800 RPM. Thanks.